the key idea of the paper is that we introduce this loss called the closest point loss, which penalizes regions of a neural implicit where the SDF properties don't actually hold, even if this region happens to be iconal. And so this allows us to produce exact neural SDFs of CSG operations and swept volumes.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today, we will be talking about the paper Constructive Solid Geometry on Neural Sign Distant Field. This paper was published in SIGGRAPH Asia 2023, and I'm happy to host the first author of the paper, Zoë Marschner. Hello and welcome to the podcast. Can you introduce yourself?
Hi, my name's Zoe. I worked on this paper while I was an undergrad at MIT, but right now I'm a first-year grad student at CMU. And this paper is joint work with my co-authors, who are Sylvia Seon, who is at University of Toronto, Derek Liu, who was at Toronto when we worked on this, but now is at Roblox Research, and then Alec Jacobson, who's at Toronto.
We have two of your co-authors were also on this podcast. So now we have three out of four. All right, Alec, you're next. All right, so in a TLDR kind of format, what is this paper about?
Yeah, so our paper deals with this class of implicit functions, which we call Pseudo-SDFs. These are functions which are iconal, but they don't obey the distance property, and we can explain kind of what those terms mean later. And they arise naturally when you're performing CSG operations. So they're a class that we run into. And these Pseudo-SDFs can cause problems for downstream tasks, especially when these downstream tasks rely on having distance-based information. We introduced a loss that we call the closest point loss. And this penalizes pseudo-SDF regions. And unlike some previous losses that were used, like the iconal loss, these can actually detect these regions and repair SDFs with this region, with pseudo-SDF regions. And so with our loss, we formulate geometric editing operations. We look at CSG operations and swept volumes. And we're able to formulate these in a way that we produce exact neural SDFs. And then also something that I think is really cool, because we're working in this neural setting, we can naturally add a latent space onto our problem. And this allows us to solve whole families of these operations by training a single network. Okay,
so this was so much information with a lot of like professional jargon that we kind of have to break down for our novice listeners. And I guess we can do that right now before we dive into the intro. So what is CSG? What is Constructive Solid Geometry to those listeners that have no idea what we're talking about?
Yeah, so I think CSG is like this, it's actually like a very classical technique in graphics. And it's a really kind of clear way to kind of do modeling with with very simple shapes. So you can imagine you take like two spheres, you stack them together, and you can take something called a union, where you just kind of take the space that they make up. And this gives you a way to like make kind of anything you want out of these primitive shapes. And so when we talk about CSG operations, we're mainly talking about four different things: unions, intersections, and differences. And you can think of these as like their analogs in Venn diagrams, if you're like familiar with set unions, intersections, and differences.
Right. I would just add that for me, I'm originally a mechanical engineer. So for me, Constructive Solid Geometry was kind of my first time, working with 3D stuff, because, we needed to design screws that fit somewhere, right? And the way you do that, you use CAD software, and CAD software is all about these Boolean operations, right? You want to create a screw, you do an extrusion, right, of a cylinder, right? And then you do like a swept surface to do the helical thread and all those kind of things. So this is super interesting. Okay, so we covered what is Constructive Solid Geometry. That's like one major topic. But the other one is the sign distance fields. I think this would be more familiar to people that listen to the podcast, because we had the paper with Derek, which is one of your co-authors, and also Sylvia. But let's make this one self-contained and tell us what are sign distance fields that you've been talking about.
Yeah, great. So sign distance fields are a type of implicit function. And this is kind of, you can think of this as something that's different than an explicit function, like a triangle mesh, because with a triangle mesh, you know exactly where the vertices of a surface are. But with an implicit function, we instead have a function over all of our space, so like all of 3D space. And at each value, we give the function, or at each point in space, we give the value the function has some value. And then based on this kind of like defines our surface. So with SDFs, the value, which are sign distance functions, the value at each point of the function is going to be the distance to the closest point on the surface. And then if we find all the points where this function is 0, so this is going to be like where it goes between positive and negative because it's negative inside our surface and positive outside. If we take all the points where this is 0, this is going to define a surface. So it's a way to define a surface, but like with this function for all space. And then, of course, there's a lot of different implicit functions we can do. Like maybe we just have like an indicator function where it's positive 1 outside and negative 1 inside. But an SDF is a specific kind, but has a lot of nice properties. And the specific property it has is this distance property, which just means that every point encodes the distance to the closest point on the surface.
Right. And recently, there's this huge trend of taking these functions and modeling them using some neural network, right? So this is why it's called neural implicit representations or neural SDFs. There are like a bunch of names that have been associated with that. But I think it's really cool to try to take this, like, I would say a bit traditional CSG, right? Constructive Solid Geometry idea and these new neural representation, these implicit representations, and kind of fusing them together into this new thing that creates these operations that we know from Constructive Solid Geometry and bring them to this new useful tool.
Oh, I'll just add like one more thing that I'll quickly add for people who aren't familiar with like this neural angle, like maybe these are more graphics-y people. I think something that really helps me here is to think of neural SDFs as just being a different way we can represent SDFs with a different function space. So a very traditional way to represent SDFs is with like a grid of values. And this you can think of like as one function space representation. And when we're doing neural SDFs, especially in like the work I'm doing, we're basically just using this really nice space of functions, which are neural networks, to represent these SDFs. So if you're scared of machine learning, like this is a very simple way to understand machine learning, just as like this function fitting problem for these sign distance functions.
Yes, this is very lightweight machine learning problem. You have this function represented as a neural network that you basically tweak the parameters to fit the underlying surface or points that you have representing the shape. Okay, so that was a lot of preliminary stuff that we had to get out of the way so people can understand what we're going to talk about. But let's go back to the intro of this paper. So what problem is this paper addressing?
Yeah, so one of the main things that we're addressing is this problem of Pseudo-SDFs, which I've vaguely mentioned previously, but now we can go into a little bit more detail about what this is actually about. And I think the way I said it before is that Pseudo-SDFs are implicit functions which are iconal but do not obey the distance property. When I say iconal, I mean that the gradient everywhere is norm 1. And you can think of this kind of as like, this is a very natural thing that's like distancy, because it means that if you take a step in a direction, like your function changes by like the same amount that you stepped. So of course, this is like what you need for something to be a distance function. And in fact, SDFs are always iconal, but this is not actually a sufficient condition to be an SDF. It's just a necessary condition. And
let's just quickly pause. What does it mean if it's iconal?
Yeah, so if it's iconal, the gradient is norm 1, like norm 1 everywhere. Yeah. And
Great,
then
sorry, go on.
Yeah. The other thing or the other factor for a pseudo-SDF is that we say doesn't obey the distance property. And so this is what differentiates a pseudo-SDF from an SDF. And the distance property is kind of just the very basic definition of an SDF, which we talked about before, that if you take a point in the SDF, it's going to give you the distance to the closest point on the surface. So the class of functions we talk about as pseudo-SDFs are these functions where they don't obey this distance property. So they're not SDFs, but they do have this condition that SDFs also have, which is that they're iconal. And we look at this class especially because it's kind of been common in the previous literature to classify SDFs as functions that are iconal, because if you because iconality is the sufficient, or is this necessary condition? Sorry. Yeah, you might be wondering why we kind of care about pseudo-SDFs at all. And the reason that we're looking at this is because these arise really naturally when we're taking unions. And I think it's a pretty, it's kind of this classical thought that taking CSG operations are really easy with SDFs, or I guess implicit functions in general, because you can just take it with there's a very simple min formulation of these operations with min and max functions. So for example, you can formulate the union as the just minimum of two SDF functions, where you're just taking the pointwise min. I think this is I learned this in some intro graphic classes and stuff. And this does give you the correct zero level set when you perform it. So if you take the union in this way, you'll get the correct surface, but it actually doesn't give you an SDF as output, even if you give two SDFs as the input of this union. So this is kind of a naive way to take unions that works in some cases, but it ends up giving you pseudo SDF functions. And that's kind of the big problem that we're looking at.
Right. So let's take an example just so it's more tangible for the listeners, right? Let's say we have a sphere, and I think you have the exact same example in the paper. Let's say you have a sphere and you have a cube, right? You put them in some overlap, one on top of the other. Both are represented as SDFs, and you want to compute the union of these two. So you take the minimum of both SDFs, and what you get is not really an SDF. It's what you call a pseudo-SDF, because it's an SDF in some places, it's iconal, but some areas you get the wrong distance. Especially if we look at the sphere and cube example, it's somewhere in the intersection of these two shapes where things start to get weird.
Yeah, so I think, this is definitely a thing that's kind of unintuitive, and it's something that I had trouble wrapping my head around it at first, because it seems like it should work. And I think something that helps me understand it is you can kind of think that, in the example you gave, where you're unioning a square and a circle, you have this union shape, which is comprised of the surface of the union is going to be the surface of the circle you unioned and the square you unioned are both going to exist on the surface of this union. But there's also regions of the circle and the square which are going to be kind of inside the union, and so they're not actually part of the final shape. And if you look at a pseudo-SDF, you can see that it kind of has these things that we call phantom level sets. Usually, I don't know if we said this in the paper, but this is what we always call them. And this is where you can kind of see the influence of the level set that used to exist in the inside of your union shape. But that's not how it should actually be, because you should have the SDF of the final union shape. So hopefully that kind of gives some intuition behind why this happens. We've talked about where pseudo-SDFs show up, but we can also talk about why this is a problem. And this is a problem you run into anytime you have a downstream task you want to perform that relies on having distance-based information. So an easy example of this is this surface offsetting task. So you can say we have an SDF that we made maybe by taking a union of something, and then we want to get the offset surface. So this is kind of a classic CAD thing that you want to do. So you can imagine it in that context. You want to make the surface bigger or smaller. And if you do this for a pseudo-SDF, you can get really bad results, even the wrong topology and stuff. But if you have an actual SDF, this is a really easy thing to do. You just add or subtract a value and you get these offset surfaces. And there's lots of other classic tasks that kind of break down a little bit when you have a pseudo-SDF where the distance property isn't met. One of these is sphere tracing, which is a way that you can visualize SDFs. If you don't have an actual SDF, you no longer have some of the bounds that we rely on to kind of get convergence guarantees for sphere tracing. So you'll still get a picture, but you won't get it as fast, and you won't get it with the same bounds. And just in general, there's a lot of things we can do downstream that rely on having distance-based information for SDFs. So when this breaks down, you can no longer do these.
Yeah, this is so the application of the offsetting that you mentioned, I think for me as a former mechanical engineer, that's super useful, right? You have this mechanical part that you want to manufacture. You have your shape, and now a machine needs to actually carve it out from this big block of metal. And what people do, right? They either plan the offset or they're like some other software that kind of measure the offset or whatever that you need because of, the tool itself has some diameter and you need to be at some distance from the surface that you want to get. So if you have this SDF information, you're kind of getting that for free, right? So this is a super useful use case. Should we talk about the main contributions of the paper now?
Yeah. So I think I've mentioned it a few times before, but the main contribution of our paper is something that we call the closest point loss. And you can use this to penalize the pseudo-SDF regions we just talked about. And this is kind of a novel loss because previously a lot of losses that were used for like regularizing SDFs were based on this iconal idea. And as we discussed, iconality is not enough to actually be an SDF. So with our loss, you're able to actually get functions that are exact SDFs, not just pseudo-SDFs. And then in addition to this loss, we talk about two different editing losses, which like in combination with the closest point loss, allow you to formulate the CSG and swept volume problems, which I think we can talk a little bit more about in the approach section.
Yeah. So your main contribution is the closest point loss, right? Which you use to identify the regions of pseudo-SDFiness and basically the editing part of the shapes. Super interesting. Can't wait to dive into that. But before we do, let's talk a little bit about related work. So which one or two papers should people read before reading your paper?
Yeah. So I think for a graphics audience, people who aren't so familiar with like all this like neural implicit stuff, I definitely recommend this original deep SDF paper by Park et al. It's, well, in terms of like neural stuff, it's a bit old now, but it's a really cool paper that really does a good job like introducing this idea of what it means to have a neural implicit and some of the problems we might consider there, like having a parameter space of different shapes. So I would recommend that one for graphics people. And then I think something that in the paper that might be unfamiliar for people who have more of a like computer vision background or a machine learning background is this stuff we do with swept volumes. I think this can be kind of a difficult problem to wrap your head around if you're not familiar with it. And so I would recommend if you're not familiar with it, we talk about it in the paper. But if you want some more background, you can look at this paper, Swept Volumes via Space-Time Numerical Continuation by Sylvia Ceylon, who's one of my co-authors, but she does a really good job in this paper, kind of giving an intro to the swept volume problem and a good example of like kind of how people solve this problem in the past. And so I think that's good if you want to learn more about like what this problem actually is and the background of this problem. And then for everyone, I would definitely recommend, this is not a paper, but a blog. There's a guy named Inigo Quiles who has this really amazing blog about SDFs. And in particular, there's a blog post called Interior SDFs, which talks about this like, pseudo-SDF idea. And it's actually what inspired us to kind of get started on this work. And I wouldn't just recommend this post, I also recommend the whole blog, which is really cool. He has like all these pages that list kind of ways to write 2D and 3D SDFs. So if you want to implement your own like analytic SDFs, you should look there and you can get like cool like stars and stuff and figure out how to write them with just math. And he also does some crazy stuff showing how you can use SDFs and like build them up into these like crazy scenes that are like photorealistic renderings. I think it's really cool to kind of see what people are doing in the like art side with these SDFs.
I'll make sure to put links in the episode description to all of these. The Deep SDF one, by the way, JJ Park was also a guest on the podcast, but not with Deep SDF. The podcast didn't exist back then yet. All right, so great related works. Check those out. Let's dive into the approach section now. So what did you do and how did you do it?
Yeah, so let's first talk a little bit more about like this closest point loss and how we actually like the math behind it. And so this loss is based on the idea of a closest point map. So if let's assume that we have an exact SDF, so the distance property is obeyed. In this case, right, we already discussed if we like pick a point in the field, the value of the function at that point is going to be the distance to the surface. And if we take the gradient of the function at that point, this is going to point, this is like a sign issue here, depending on whether we're inside or outside. But essentially, like this gradient will point either directly towards or directly away from the surface. And so we can from this information get an arrow that points us towards the surface and the distance to the surface. And if we kind of combine that information, we get exactly the line we need to walk along and how far we need to walk along the line so that we'll arrive exactly at the surface. And so if we're in an SDF, we can pick any point in our function and applying this like closest point map, we should arrive exactly on the zero level set. And so if we map a point, we get a new point through the closest point map, and we evaluate this point through the same function, like the SDF function. We should then get 0 because we're at the zero level set. But if you instead start with something that's not actually an SDF, so it's like a pseudo-SDF, say, and you apply the same closest point map, you'll find that some point you pick after applying this map, you don't actually end up at the zero level set. And so if you apply this point, you get a new, like a mapped point, you then put that through the function, you're going to get something that's not 0. And this is an indication that your function is not an SDF, because like this closest point map kind of encodes the like idea of what an SDF is. And so when it doesn't work, it gives you points that are not along the zero level set. It means you have sections that are not actually encoding the distance property. And so we can make this into a loss by kind of like the way we do it is sampling a ton of like sampling points around our domain, mapping them with the closest points map, then putting those points through the function and getting some values. We square them because they could be negative, and then we just add them up. And if this differs from 0, right, it's not an SDF. And so that just gives us a loss because we can minimize that to go towards an SDF. Does that make sense?
Yes, makes a lot of sense. Let me just quickly recap because that was a lot of detail. Let me be a little bit more kind of figurative, right? So let's say I choose a point somewhere in my domain, right? I chose my point. Now, because this is an SDF, the gradient tells me where the surface is. So now I get an arrow that I can walk. If I walk along that arrow, I can get to the surface. But how much I need to walk in that direction is exactly the value of the SDF, right? Because it's the distance. And if it's a true SDF and I walk in that direction for that distance, I'll hit the surface. But if I'm in a region where it's actually the pseudo-SDF or where it gets the distance wrong, I'm not going to land on the surface. I'm going to land in somewhere else where it has a different value, not 0. And then I can use that value in the loss, right? This is what you did, right? You put that value in the loss, and if you try to minimize that, now you're basically pushing those areas where it's not an SDF to be an SDF.
Yeah, exactly.
Cool.
Yeah. And so this acts kind of as a regularizer, because if we minimize this loss, it pushes us towards getting these exact SDFs. We also, in our, like when we're running these experiments, we also add in the iconal loss, which we talked about before a little bit, but the basic idea of the iconal loss, which is previous work, is it's this loss that, I mean, it's not a constraint, it's like a soft constraint, but it essentially constrains the gradient of the points we sample to be 1. So you can just formulate this constraint as a soft constraint. And we need to add this loss in because otherwise there's kind of this nasty minima to the closest point loss, which is that if you make everything 0, this is actually like this is a minimum of the closest point loss, but of course that's not what we want. So if we just add the iconal loss, we can prevent this thing from happening where everything goes to 0. Yeah.
Right, and we should mention that the iconal loss, I think, was first introduced by Grop et al., Amos Grop, yes, and Yaron Lipman's group. Great paper, really liked it. IGR, I think, is the original name of the paper. Really cool. So this is another regularizer that you're using.
Mm-hmm. Yeah, so we combine those two regularizers to get like our final regularizer for exact SDFs. And then we add this together with what we call like editing losses, which are the things that actually kind of encode the like geometric edits that we want to make. So let's first talk about the CSG operations. So talked about this before, but these are like unions, intersections, and differences. And you can think of the problem here as kind of being just trying to repair pseudo-SDFs, because I guess the setup for the problem is we're handed like a set of implicit functions and how you want to union or intersect or difference them together. And using this, we can kind of construct with the min and max, like naive method, we can construct the pseudo-SDF. And then if we kind of formulate that as a loss function, or I guess we can formulate a loss function based on the pseudo-SDF, which just encodes the intuition that if we have a pseudo-SDF, and we want to get like the actual SDF for the CSG operation, the thing that we know based on the pseudo-SDF values is that every value in the correct answer should be at least greater than the pseudo-SDF value. This is kind of, if you're familiar with like conservative SDFs, this might seem familiar to you. Conservative SDFs are these like, the intuition that we're kind of encoding is that because we have this iconality of the pseudo-SDFs, we know that the actual value of our function is going to be greater than the value that it is in the pseudo-SDF. And we can just kind of write a loss function for this, add in our regularizers that we already talked about, and together these give you a way to like repair these pseudo-SDFs.
Right. So just to make sure that I understand correctly, right? So you have your SDFs, you apply the CSG on them, right? You get this new pseudo-SDF, and now what do?
Yeah, and so you have this pseudo-SDF, which is in kind of like the input data. The input data is the data that allows you to create the pseudo-SDF. And we then kind of do like a traditional like neural network training where we kind of stochastically sample some points around our domain. There's some details to point sampling, which I think we can maybe leave. The listeners can go look at the paper if they're really interested in this. But we sample these points. At each point, we have like a set of losses. One of these losses is the CSG loss. And so for the CSG loss, we look at what that point should be in the pseudo-SDF. And then we want to constrain, or it's again not a constraint, it's like a soft constraint. But we want to encourage the network value at that point. So the value of our like training neural network, we want to encourage that value to be greater than the value in the pseudo-SDF because we know that this is true. And then with that constraint and then the added addition of like regularizers, we like the CSG constraint kind of just tells us like make sure that we get kind of geometrically the CSG operation we want. And then by adding the regularizers in, we get something that's also an exact SDF.
Right. Okay. Let me try again. So you take your SDFs, you apply a constructive solid geometry operator on them, right? Some union or intersection or whatever. You get your pseudo-SDF. Now you train a network that basically takes that as input, and you use your regularizers and this new CSG loss function to encourage it to become an SDF. Now, do you do it on a single example, or do you basically now have a network that takes any pseudo SDF and turns that into an SDF?
Yeah, so I guess like the most basic example of like a single example, or the most basic kind of problem is doing this with a single example. We can talk a little bit later about how we can expand this to doing multiple examples. I think that might be better suited for the results section. But yeah, in this case, but we're not just training it for one point. I guess we're training it for kind of the entire field, so 2D or 3D. And maybe I should have mentioned that like the architecture of the network, which is like the kind of classic architecture of a neural implicit, is that at the input of the network, we're giving it like a spatial point, so like x, y, like where we want to evaluate the network, and the output is going to be a single like scalar value, which is going to be the SDF value there.
Right. This is why they sometimes call this coordinate networks, because they get coordinates as input and you get the output as the distance that you want, right? The sign distance value, so a scalar. Yeah. Okay. So in the most basic setup for any sign distance, like neural implicit representation, right? You get your points as input, you get your sign distance function as output. Basically, all of the shape is encoded within the network. And your surface is basically the zero level set of that, right? So in your setup, instead of just taking a shape, you're basically taking a constructive solid geometry, right? You're taking a pseudo-SDF that was constructed by a union or whatever Boolean operator that you applied on the input primitives.
Mm-hmm. Exactly.
All right, what next?
Yeah, so now let's talk about the swept volume problem. So you can kind of think of swept volumes as like very similar to the CSG problem, because a swept volume is essentially an infinite union. So it's like a union of a shape along a path, and you're doing this infinitely. So this is we can in some sense, like these are very similar problems, but there's some differences. So we have to treat this problem differently, and we'll talk about that now. First, let me talk a little bit about kind of like what the swept volume problem is for people who might not be familiar with it. So kind of the basic problem that we're considering is this problem of having a shape and a path. And the shape you can imagine is moving along the path. And we then want to compute kind of the resulting shape of all points that this shape touches as it moves along this path. So as I mentioned, it's like the infinite union. And a good example to have in mind here is like one place by swept volumes I use is in like 2D drawing, like in Photoshop. So in Photoshop, you might have a brush and you kind of like draw stuff with the brush. And the output is like every point you touch while you were drawing. And so this is an example of a swept volume where the shape is the like brush that you're stroking, and the shape is like, or the path is kind of the path that you trace out with your mouse as you're drawing. And the like naive method for solving swept volumes is to do something that's called stamping, where you just kind of take n, like take the shape and then like take n copies of it along different points on the path, where you want n to be infinity, but that's not practical. So you choose like as big of a number as you can before it gets like computationally inefficient. And this gives you like an approximation of the swept volume, but not only does it have, and then you union all of those stamps together. And this, again, has the same like pseudo-SDF problems that we talked about before. It's not going to be as SDF. And it also has this problem that like, when we do this, it's not actually an infinite union. So you end up with like artifacts along the edge where you didn't take enough stamps. And if you take like just a few stamps, of course, you'll get like nothing. You'll just get like 2 stars if the shape is a star. Yeah. And I think it's important to also understand kind of how we would take this problem and actually pass it into like our neural network training like setup. So I guess the input to this.
Let me just quickly throw my 2 cents into the mix. So the sweep volume, I remember back from my undergrad years, right? We had this assignment where we needed to model it wasn't a roller coaster, but something that looks like a roller coaster or like a water park slide. You know how they can like you have this weird path like that they take, and basically what you do, you get like these. Well, this is 2D, right? Not a solid, but we did it with like a 2D semicircle, and you kind of pull that or sweep that over the path to get that slide, right? So this is maybe something that people can relate to, right? If you look at if you go to your nearest water park, look at the slide. It looks like a semicircle, half a circle that somebody just pulled or like swept over a path. Okay, but so how do we now connect this infinite number of stamp solids into your? Well, you're not doing it with an infinite number, right? You have a better way to do it with your setup. So how do you do it?
Yeah. Great. Yeah, that's a really cool example too. So thanks for that. But yeah, let's talk about how we would actually like pass kind of this problem setup to our network. So we do this with something that we call a space-time function, which is not as fancy as it sounds. The basic idea here is that we just kind of define a function that's over kind of the same spatial coordinates we had before, so like x, y, and it's also over a time coordinate, which is just the time along a path. And if you look at any like one time, like we look at time 0, we put 0 in for the time, and we kind of look at the resulting function. This is just going to be an SDF of the shape at time 0 that we're like sweeping along the path. And you can just do this for any t, and that kind of gives you the shape swept along the path. But something that's important to note here is that this is like a really kind of it's a really general way to represent this, because we're not just passing in like a shape and a path. We're passing in the space-time function. So we can have any path we want. It doesn't have to be like linearized or discretized or anything. We can have like curves. We can have lines if we want. And we can also have kind of any shape. We can have a shape that's rotating along the path. We can have a shape that's actually changing shape. So we could change from a square to a circle along this path. We can represent like any change like this along the path. So this is a really nice way to like pass this in, because it doesn't really put any constraints on like the kinds of swept volumes we can compute. Yeah. So
really cool. So basically, what does it change in the setup, right? So instead of having X, Y, Z, now you have X, Y, Z, T.
Yeah. Well, this is actually something that's maybe a little bit confusing. That like we have kind of like we have one function which is like what we're passing in, and this is kind of like analogous to kind of remember how we talked before about how we pass in like this pseudo-SDF. for the CSG operation case, which we can construct from like the input like couple shapes that we want to union together. In the swap volume case, we're going to be passing in this like XYT this XYT function, which is like mapping from XYT to a scalar. That's the spacetime function. But what we're trying to compute is like actually the exact same dimension. We're still trying to compute something that goes from XY to a scalar because like the resulting swap volume is no longer like, doesn't have this time dimension anymore. So our model is never like our neural network model isn't going to have this time dimension, just like the thing we're passing in, which is like the truth that we know that's going to have a time dimension.
Right. Yeah. So you're still mapping from either R3 or R4, depending if you're in 2D or 3D, into R1, right? So scalar.
Yes. Yeah. And so the swap volume problem is a bit harder than the union problem. And I guess a way to imagine that is if you imagine you pick a random point in the Pseudo-SDF case for like a union, and the point is positive, which means it's outside the shape, then you know that this point is definitely like positive in the final shape. So you know this is a point that you picked that should be on the outside of the resulting shape. But in the swap volume case, if you pick a random point in your spacetime function, like the input function, and it's positive, this actually doesn't give you much information because you could have picked a point that's positive that is on the outside of your like final swap shape that you want to get. But you could have also picked a point that's like positive for this time, like where time is like the extra variable from the spacetime function, but it's not actually positive in the final shape because maybe the shape just isn't there at this time, but later it will like pass to that point. So this is actually something this is kind of what makes the swap volume problem harder than the CSG operation problem.
Right. Interesting.
And yeah.
How do you overcome that?
Yeah. So to kind of get around this with our losses, we introduced two losses, one which encodes the intuition we can have about the interior, and one that encodes kind of what we can know about the exterior, because you'll see that we know different things about these two domains. And when I say interior and exterior, I mean interior and exterior of the final like swept shape that we're trying to get. And so in the interior, we know kind of a lot. I guess the main thing that we can use to kind of formulate this loss is this idea that if we pick a point from the spacetime function, and that point is negative, which means it's in the inside of like the shape that we're sweeping along the path for that time and point in space. So if we pick a point that's negative there, we know that the final point at the same point in the final network, like the network of the swap volume, the point or the value in that network should definitely be smaller than the value of the point that we sampled from our spacetime function. And this is just because like if we ever get a negative point in the spacetime function, right, we know that like this is definitely going to be inside, and in fact it's going to be at least this distance inside the final shape. And that gives us like kind of a lot of information, enough to formulate this loss that gives us a good way to determine like which of the points that are in the interior of the swap volume. So this is like one half of the losses that we add. So we add this loss. Does that kind of make sense?
Yes, makes a lot of sense. Do go on.
Great. Yeah, and so in addition, you could imagine we just have this loss, and there's a problem we'll run into, which is that we've never said that anything has to be positive. So the network can just, it's going to do whatever it wants, and it will want to just make everything negative. And so this is a big problem for us. And we have to come up with some way to also encode what we know about the exterior. But I think, as we discussed before, we don't know so much about the exterior. But one thing we can encode is the idea that if we haven't, if points are not like constrained to be negative, like if we never say in this loss that they should be negative, then they should be positive, because that means they're probably outside. And this is kind of the idea of if you were trying to compute the swap volume by hand, maybe you like first like draw in the part that's going to be on the inside of this, like the part that's actually the shape swept along, and then okay, everything outside is like going to be the positive part. So you could just color that all in positive. And so to get this to actually like be a loss that we can add to our network during training, we just have this like kind of ambient loss, which just says that everything should be positive with a pretty small weight. And so this is able to achieve kind of what we want, which is to set everything that's not set negative by the interior loss to be positive.
All right. So it's a great bridge to start talking about the results section. So how did you evaluate this?
Yeah, so we came up with a lot of like experimental setups where we can show examples of using these CSG operations and these swept volumes to actually like solve some real problems that we came up with. We show visuals of like the results we get here. In some of the figures, we show like visual comparisons with like the pseudo-SDFs that you get with the naive method and the exact SDF that's like the ground truth. And we have a few like in one figure, we're showing like quantitative results that kind of show that our stuff is closer to the ground truth than the pseudo-SDF, which you can kind of also see visually. And then we also we show like some failure cases where like if you have a pseudo-SDF and you like apply the surface offsetting problem, it'll like totally break. But with ours, we don't have these same problems because we have an exact SDF, so we're able to do the surface offsetting exactly. And I think that's like the general way that we kind of can evaluate our method. And can talk a little bit about some of the cool experiments we come up with to show where you'd actually use this method for like they're not really real problems, but they're like realistic problems we came up with, which I thought were cool. One of my favorites is this problem that's kind of dealing with how we might apply. I guess we actually talked earlier about how you can use these CSG operations in CAD, and we modeled this like pin shape with our operations, which is kind of similar to how we talked about before. Like these CSG operations are really good for like making CAD models, and this is a really cool example because we're doing something where we have a latent space. So I can talk a little bit about what that means because it's a great application of our method. So a latent space is this neural SDF thing where in addition to passing in the coordinates to the network, like we said, we can also pass in some additional values, like kind of any number of them. And with these values, we can create like a couple dimensions of like a latent space. And then the output of our network is then kind of conditioned both on the coordinate we pass in, but also on the latent code we pass in. So it's like an example in the deep SDF paper that we talked about earlier, where you kind of can train a network to have different chairs at different places in the latent space. And then as you look at different latent codes, you'll end up with like different interpolations between these kinds of chairs. Like that's the general idea here.
Yes, basically this latent space, this latent vector, this set of values represent the instance or the specific shape that you trained with, right? So every vector represents a shape. So if you condition the network on that vector, you basically get the surface of that shape.
Yeah, and this plays really well with our network because it allows us to, instead of just training like one network and getting the result of kind of one CSG operation or swept volume, we can train a network with like a whole latent space and get the result of many CSG operations or many swept volumes. So in this example I talked about where we make like this CAD model, I guess I made this model that like is a union/intersection of these three different shapes. And then I made this model parametric. So there's some like variables like the heights of these shapes that I want to be able to change. And so I make a latent space for my model that's like 4-dimensional that kind of is different. Like as you go through this latent space, you kind of change the like input, the dimensions of these input shapes. And we can train this model once to get the CSG, like using our CSG loss, we can train this to get the exact neural SDF for the CSG result. And then once we have this model, we can kind of look through the latent space of the network and explore a lot of different variations on one kind of design of this little shape. You can look in the paper. There's like
that's really cool. It really kind of like putting on my vision cap on, right? We always have this question about generalization, right? How well does it generalize, right? And with all of these neural SDF works, right? You're usually, or like most often you train on like one shape and you get that, right? But in this case, you say, well, we can work with latent codes, right? And we can train that CSG with those latent codes and it works, right? You don't need to retrain for every set of primitives or CSGs that you have, as long as you kind of train it once in this kind of latent space. That's really cool. Like the latent space that you trained, was this like Derek's Lipschitz space thing or just the general like original?
Yeah, I think this is actually something that I think would be cool to look into more, how we can come up with different like spaces for these latent codes. For our work, we're actually not doing anything where we're not generating the codes like you might in some of the other work that's doing latent spaces. We're just literally passing in like this vector of like heights of the different shapes in our initial like CSG, or just like different parameters of the shapes that we're performing the CSG operations on. So it's really direct. We're just like passing in these numbers that just parameterize the shapes. And I think there's a lot of
I see. So this way it's already right, because basically when you train it from scratch, right, then your latent code, it's the interpolations between latent codes are not continuous in the shape space, right? You had these kind of jumps and stuff. But if your latent codes are basically those parameters, then it's like you can interpolate as much as you want. It's predetermined.
Yeah. Yes.
Cool. Okay. Were there any kind of unexpected results?
I guess before we talk about that, I'll just quickly mention the other kind of application of latent codes, which is really cool, which is for the swept volume case. So we talked about how we can solve this swept volume problem. And we show some results where we don't just solve one swept volume problem, we solve like a whole number of them parametric over some variables on the path. So this is really cool because it lets you like one thing we show is where we are totally parametric over the path, where we kind of can pass in parameters of just like the shape of the path to parameterize this space we're using like the cubic Bezier control points. And so when we train a network like that, we can pass in like any path after we've trained it and get the output of the swept volume along this path. So this gives a way to implement, like we've talked a little bit about this, like drawing in Photoshop as an application of swept volumes. So I guess an example we can do with this this network that we train parametric over the paths is we can just like draw whatever we want with Bezier curves and then apply our model, and without having to train it, we can kind of get an output of this drawing. So this is I guess cool because we often want to kind of do something like this where we have one shape that we want to sweep, but we want to look at it over many paths. And so with this latent space, we can get that. We also do this in 3D, which is fun because the application of like 3D swept volumes is, well, one of them is for drawing in VR, like in these VR drawing things. And so we show some examples in the paper that are showing this like with actual data we collected from VR, we're showing these like 3D shapes swept along those paths, but we only have to train one now.
Bunny, right? Stand for bunny along a path. That was one of them.
Oh yeah. We do show that, like this, the 3D Stanford bunny, like with some rotations along the path and stuff. Yeah.
Well, every graphics paper has to have the Stanford bunny.
yeah. We had to put it in there somewhere.
What's the name
Spot,
of that cow? Spot. Yeah.
I don't think we have a Spot, but.
No. Yeah. Your current supervisor would be upset. No, I'm joking.
Yeah, now that I'm at CMU, every paper has to have a Spot.
Okay. Were there any unexpected results?
Yeah, I don't think there were necessarily like anything that I found super unexpected. I thought it was like so cool when I finally got this working, and like the first time I could see like scrolling through the parameter space and like looking at all these different shapes that all looked really nice. And yeah, not that it was unexpected, but I thought it was like this super great moment for me to actually see that I was able to kind of get all this interesting geometry with like this one chain of the network.
Any notable fail cases?
Yeah, so I guess in general, this model definitely suffers from a lot of like neural problems that exist in a lot of neural implicit methods, or just like that are inherent with neural implicits. One that really bothered me and is important for kind of the cases that we're visualizing is the fact that neural implicits generally kind of have difficulty getting sharp features. And so you can imagine when we're trying to visualize stuff, we actually do have a one figure with Spot in it. I forgot. So we do have Spot in our paper. Yeah.
Okay, Keenan won't be upset.
Yeah. Yeah. I guess Spot's a good example of this. Like Spot has these little ears, and when we want to train like a CSG operation involving Spot, we want to make sure we can see his ears. And since these ears are sharp features, it can be hard to get this. We talk about a little bit in the paper how we can kind of get around this with some pretty simple methods for like changing our sampling schemes. But this is definitely something that, right, there's a lot of work in neural implicits getting rid of making sure we get sharp features. And I think we struggle from a lot of the same things people have discussed before, where, you know, we can lose a lot of sharp features, and it's a shame that it's not kind of like like we really kind of want these for a lot of the things we're looking at, because, we end up with these models that have sharp features, these CAD models have sharp features and stuff.
Yeah,
and
I think yeah, sorry, let me just interject here. So I think the problem with sharp features is basically like it's rooted in the iconality of the functions, right? Because in order to have the sharp features, it means that you need to have a point, or sometimes even a whole medial axis kind of thing, where the iconal term doesn't apply, right? It's either a point where it abruptly changes directions of the normal, or something like that. And this happens all the time when you have sharp features. And this is why a lot of these methods have an issue, right? Because these are points where the iconal term doesn't hold, and you're still trying to force it to hold, and it's kind of like a whole mess.
Yeah, that's exactly right. There's like this small isolated strip where we want to have the iconal term, like, well, the gradient should be undefined. And I guess this shouldn't be like, right, this should be like just like a single line, but of course it can be really hard for the network to actually get this. But there's also like another factor that's working against us here, which is that like, because we're doing this all kind of stochastically, like sampling points stochastically to train these, it can be hard to sample the correct points, which are the ones like in these sharp corners. And I'll actually say this is especially a problem for these swept volumes, because we're kind of working in this like lifted space-time space where like we're one dimension above. Some things that might look like sharp features in like in a swept volume actually are sharp features. Like if we sweep a like star along a path, like not only are the points at the end of the path where we like can see the pointy bits of the star, like those are sharp features, but actually the entire edge of that path is a sharp feature, because in the input space, like every single point that lies along the edge of like the swept star is going to be like at the corner of a star. And so this is especially an issue in swept volumes, because things that look like straight lines are actually sometimes sharp features in the space that we're sampling from.
Right. Yeah. I think the whole question of how should we sample in order to train proper neural SDFs? I mean, it exists in many papers, like in your paper, I think also in some of Lippmann's group paper, they also kind of tackled this problem. I think it's interesting, right? Like, how should we sample to make things work properly? I think you guys tackled it nicely. They tackled it nicely. But to me, it's an open question that people kind of need to pause a minute and kind of ask, okay, how should we sample? What's the best way? And I don't think there's like a fully correct answer yet.
I'm very interested in this problem, because it feels like there's so many like different kind of intuitions we can think about where might you want to sample. But I think it's really interesting to think about how we can actually like make methods for sampling, like where we intuitively think is best. And I don't know, there's like so much literature about sampling. So I think it's definitely something that when I was making this, I was interested to like read through kind of what do people do for sampling, and how can we effectively do this?
Yeah, which brings me to the next part of the episode, right? Conclusions and future work, right? So one possible future work would be exploring the sampling, but how do you see the impact of the paper going forward? And have there been papers like that build on top of this, or which interesting projects do you see going forward after this?
Yeah, I guess, well, this paper is very recent. It's not even really like officially publicly presented yet. So I guess we have a lot of time for future work. Something that I'm really interested to see is whether we can use this like loss function we introduced, the closest points loss, in other problems, and whether it kind of can give us the same benefits in other problems. I guess one example is like there's this problem where we want to kind of fit an SDF to a points cloud. I think it would be really cool to kind of see like what happens if we put the closest point loss in there? Does that help us get like an SDF of a point cloud? How does that affect solving the problem? And in general, I'd be really, really excited to see kind of follow-up works that are able to like use this SDFness in the neural, like with neural implicits to actually like do cool stuff that relies on the distance property in neural implicits, which I think like kind of in the past with neural implicits, it can be kind of hard to like trust that the distance property ever holds, because it's really hard to constrain these things. And I think it would be really cool to see some stuff that is able to actually use this important property with these neural implicits.
Yeah, super interesting direction. I think like this space is Well, generally, all of the neural implicit space has been exploding in the past few years, and I don't think we're done with it, right? There are so many things that are not solved yet. So I think it's a really interesting direction, place to be. Which brings me to the final and my favorite part of the podcast. What did reviewer 2 say? So can you please share some insightful comments you had in the review process?
Yeah, I think the reviews for this paper were overall really good, really nice, and awesome feedback. We published it at SIGGRAPH Asia. So this is like the SIGGRAPH review process. We got, I think they do like 5 reviews or whatever around that. And all of our reviewers were really detailed and helpful feedback. They seem to really like this idea of having this novel loss, the kind of mathematical background of it. And I was glad to hear that because that's kind of the part of this that I really like too. One thing that I was really excited about from the review process was that a lot of the reviewers wrote that they kind of thought that, like, why do we care about not having a pseudo-SDF when it only matters for surface offsetting? I thought, oh, shoot, we meant to say that like it matters for a whole bunch of things, but we really focus on the surface offsetting problem because it's really intuitive and easy to understand. And like when we were actually like working on this paper, we talked so much about kind of like all these different reasons we might want to use like the distance information and why we might need to have an exact SDF. And we definitely realized after we read these reviews that maybe we didn't do a good enough job kind of highlighting this idea that we talked about so much. So this definitely taught me that just because you talk about it with your collaborators a lot, you got to make sure that you really like hammer these points home in the paper. And so we added some stuff to the final version, where we try to really highlight this idea that there's a lot of things that you can do with SDFs when they have this distance property that you can't do with like pseudo-SDFs.
Yeah, I think what you just mentioned about the review process, I think this is like I call it the zoom in, zoom out problem, right? When you're working on a paper and you're so focused, like you get this kind of tunnel vision, you're doing what you're doing, you see that everything is obvious, right? It's obvious that it's applicable to this and that and everything. And then when you come to write the paper, then you're like, because those things are obvious, you don't even notice that they're missing. And this is why it's so good to have this review process where you kind of get it highlighted, like, oh yeah, there's this and that, and maybe elaborate. And this is a great reason why the review process is there, right? To make the papers better for readers that, they don't live in our heads, right? It's so much easy to get like so tunnel vision that you kind of forget to write stuff. I still do it, it's something that I think maybe over time it gets better.
It was also, I guess, useful for me as someone who's like, I have a graphics background, so I'm familiar with the graphics ideas in my paper more. And so when the reviewers wrote their reviews, they included things that they were like confused about. And that was really useful for me because when I was preparing the revision, I went back and every part where they said they were confused, I was like, I got to reword this, even if it makes sense to me, like make sure I really expound on it. And that helped me like pick up points that I hadn't realized would be more pain points for people, which I was able to expand on. And hopefully now like the paper is more understandable to a wider audience because that's always my goal.
Yeah, it's a great paper. I had a good time reading it.
Thank you.
So, Zoe, thank you very much for being a part of the podcast. And until next time, let your papers do the talking.
Thank you for having me.
Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.